Hello students, today I will discuss excess pressure on the liquid surface. Let us start the topic excess pressure of liquid surface. Let us consider a molecule O on the liquid surface. The liquid surface may be the plane surface, the convex surface, and maybe the concave surface. If the liquid is on molecule is O on a plane surface, the surface tension T is applied in both the sides and they will cancel the force in both sides. Similarly, other surface tension on the plane. Hence, the pressure inside the liquid and the pressure from outside the liquid will be equal. The inside the surface and the pressure from outside the surface is equal. It is Pi or Po. Hence, there is no excess pressure because Pi is equal to Po. But in case of the convex surface, here is the convex surface made by liquid. The T is the surface tension on the point molecule O, and T is this side also. The resultant force by using law of parallelogram will be the diagonal force, and this is the resultant force due to surface tension is applied on the molecule O, which is vertically downward. But the liquid surface is in equilibrium. The O is in equilibrium. So this force will overcome by an excess pressure. It means pressure from inside the liquid is more than pressure from outside the liquid. Similarly, in case of concave surface made by the liquid, the point O molecule will have surface tension T and T. The resultant force will be the diagonal of the parallelogram, and the resultant force is upward because of the surface tension. But again, the molecule O is in equilibrium. To make them equilibrium, the upward pressure should be more than the lower pressure. It means the Pi is lesser than Po. Hence, the excess pressure here, if Pi is less than Po, it means excess pressure is vertically downward, which equalize the force due to the surface tension. So if we say here is the surface made by the liquid, it is concave. If we see from this side, from the liquid side, the excess pressure will be on the concave side. Similarly, if liquid is here, the excess pressure will be on the concave side. So the excess pressure make concave surface. Right? Now the next point, we will discuss the excess pressure in different situations. For example, first of all, we take the liquid drop. Now we calculate the excess pressure inside a liquid drop. You know, the liquid drop is a spherical surface and liquid is filled inside this one like this. I am making it by green dots. So the concave side will be the liquid side. Hence, this is the excess pressure. It means the pressure applied from inside will be more than the excess pressure applied by the outside. Here, Pi is more than Po. That's why the liquid will make the concave surface. Here is from, if we see from the liquid side, here is the concave surface. If R is the radius of the liquid drop and T is the surface tension, the Pi is the inside pressure and Po is outside pressure, then the excess pressure, we may write it at P or we may write it as a delta P as well. The excess pressure will be Pi minus Po. We have to find out this excess pressure. Let us consider this excess pressure change the radius. This excess pressure delta P change the radius of this sphere, the liquid sphere, by delta R. The new radius will be R plus delta R because of the surface pressure, in excess pressure. The work done will be there because of this excess pressure, and we know work done is equal to force into distance. Force is pressure into area, into distance is delta R. This P is excess pressure. A is 4 pi R square. You know the surface area of a sphere is 4 pi R square into delta R. This is equation 1, right? Now, we may say this work done is stored in form of potential energy. And this liquid drop has a single surface. This is liquid drop and this is surface. It has a single surface. The increase in area of the drop will be 4 pi R plus delta R square because the new surface area is 4 pi R plus delta R square and initial area was 4 pi r square. We may take out 4 pi, and now we may open the bracket also. By using the formula a plus b whole square is a square plus b square plus 2ab. So it is r square delta r square plus 2r into delta r minus r square is there. This minus r square plus r square is cancelled. As the radius increases, is very, very small than the actual radius of the drop. It means the delta r square is negligible. The square of the small quantity will be negligible. So we may neglect them. Hence, the increase in area is 4 pi into 2r delta r, or it is equal to 8 pi r delta r. Why we are calculating this change in area? Because we know the surface energy is equal to surface tension into change in area. We already derived this equation and also solved the numerical as well. So we able to find out delta A here, and this delta A is 8 pi r into delta r. So because of this work done, there will be the change in energy of the liquid drop, and which is stored as a potential energy. This energy will be stored in form of potential energy, right? We will use this formula. The surface energy is equal to surface tension into change in area. Surface tension is T, and change in area from using the equation number 2. It is 8 pi r delta r. And this is equation number 3. This increase in potential energy is because of the work done by the excess pressure. Work done by the excess pressure. So we may equate this one. That is, we may equate the equation number 1, 4 pi p r square into delta r is equal to 8 pi t r delta r. Delta r will cancel. The square of r will be cancelled. Pi will also cancel. So we will get the excess pressure is equal to 4 to 8 2t upon r. This is the excess pressure of a liquid drop. Excess pressure of a liquid drop. And this is important derivation for exam purpose also. The question may be asked as find out the excess pressure on a liquid drop. The excess pressure will be inversely proportional to the radius of the drop. It means the smaller the radius of drop, more the excess pressure. So pressure will be more in case of small drop than the excess pressure of a big drop.